Hello and welcome to our lesson on the global air circulation model. Today our three key takeaways are to describe the movement of each of the air circulation cells, to explain what the climate would be like in different places and why it is like that, and to link certain biomes to these different areas of latitude. Okay, so that'll be our focus for today. Make sure you have something to write down, make annotations. This can often be quite a tricky topic, but if you break it down bit by bit, it should simplify that. So our global air circulation. So what I've done, I've got a diagram just on the left, which shows the different cells that we can have. Okay, there's also a little image just on the top right, which basically shows two different boxes of air. Okay, I will label this as high pressure. Okay, so high pressure air, and what I'll do, I'll just shrink that box a little bit. So if you imagine, if you pump up a tire, you fill it full of air, you want it to have a high air pressure, it's going to be much greater. Okay, going to be full of air. Okay, which you can see in that box, there's more air particles. Okay, so then we've got the other box, which is going to be low air pressure. If your tire, well, I'll do low pressure air. If your tire is a little bit flat, you would say that it has a low air pressure side of it. Okay, there's not much air inside of it, okay, which you can see in this box here. Okay, now ultimately the air circulation comes back to two different things, so just bear this in mind. High air pressure, just imagine air in that box full of air particles. Because there's more air, just consider it to be heavier. Okay, and then with the low air pressure, just consider it to have less air in that space, so it is lighter. And if you follow these two different ideas, it should connect everything together quite nicely. So I'll just highlight these so they're just together in their space. Okay, and we'll highlight the second one. Let's do it as a red. Okay, so we'll keep hold of these ideas. So first of all, we'll start with these different cells. So we've got the Hadley cell, which we'll highlight. We've got the Ferrel cell. And we've got the polar cell. Let's do that as a blue. Okay, so these are our different climatic cells, okay, or our different cells with different movement of air going around the world. Okay, now in theory as well, our Hadley cell isn't just one, it's this one and is that one there. Okay, so what we'll do is we'll just go back 2 steps. Okay, so we've got these different cells. We'll start off with the Hadley cell. Now, obviously we know we're on the equator, and if we imagine our sun is over here, okay, I'll just put that as a big glowing ball. Its solar radiation comes in. It's always going to be more intense on the equator. Okay, if you warm something up, the air particles will expand apart. So that's what I've kind of linked to on the top right diagram here. Okay, so as something is warmed, the particles will be given that energy, and this is happening with air rising. Okay, so air is warmed and it rises high up into the atmosphere. And as it gets into the high atmosphere, it will start to create clouds. Okay, I will mark this in as a gray. So it will create clouds across here. So that basically creates a whole lot of rain. Okay, so the equator basically is creating its own ecosystem where its intense heat will cause air to rise. And as that moist air rises from the equator, it will create its own weather patterns. Now, this air is going to be spreading out, can't go into space, so it spreads out across our atmosphere. Okay, gradually becoming colder, gradually losing its energy, and gradually the particles are starting to come together. Okay, which is where we link to this box here. So the particles are starting to contract together, losing their energy. They're not expanding far apart, they're contracting together because they're in the cold reaches of the atmosphere. They've lost all of their energy. Then that air will start to become heavier and it will sink back down. Okay, so air only creates clouds when it rises. So air that sinks doesn't create clouds. Okay, so this will lead to certain things happening on these two places. So we'll make a quick note here. On the equator, air rises due to what we call convection. Okay, which is where heat is transferred to the air, causing it to rise into the atmosphere. Okay, and this is because the warm air is expanding and becoming lighter. Okay, so a few key points there. So I'll just highlight these. I'll highlight them in red because we're talking about what's happening. So first of all, we're talking about convection. So the heat from the sun is transferred to the air, causing it to rise. Okay, so it rises on the equator. This is because warm air is expanding and it's becoming lighter or less dense. Okay, so this will create clouds. Rise in air creates clouds which rain or precipitate. Okay, air will spread out across the edges of our atmosphere, losing energy as it spreads. Okay, so we'll highlight a few key points there as well. So I'll just move it down a little bit more. So here, so the clouds will rain. Okay, the air will spread across the edges of our atmosphere and it will lose energy. Now, as it loses energy, particles will condense together. So I'll put this point up here. The air loses energy, particles condense together, come in denser, and sink in downwards. Which is exactly what we can see there. So now we're switching to a different color. So we're looking at more blue aspect. The air loses energy, it condenses, and it becomes more dense. Okay. So we'll just link to two different things that we expect to find with these. So low pressure, and I'll write this in red. Low pressure, where there's less air, it's lighter, the air rises to create clouds. Okay, that's an important point. So air rises to create clouds. So anywhere where there's clouds or rain, you know you're looking at a low pressure environment. I'll get rid of that. And then if we are looking at our high pressure, I'll just put this point over here. Air is denser, so heavier, so it sinks. Therefore, no rain. And this will give us a few clues later on of what kind of biomes we're going to be expecting in these places. Okay. So therefore, if we determine what kind of air pressure systems we have on the equator, we would say, well, air is rising, therefore it must be lighter, low pressure systems. And if we say on the equator, air is, on the 30 degrees latitude, air is sinking, that must mean that we are looking at more condensed or denser high pressure system. Okay, brilliant. So if we use this idea, so anywhere where air is rising, it's low pressure. So actually, on 60 degrees latitude, I could put that is a low pressure system. I think I just need to replicate these points. So 30 degrees south of the equator, we've got high pressure. 60 degrees north the equator, where you see the ferrule cell meeting the polar cell, we've got air rising, so that's got to be low pressure. And same as replicated 60 degrees south of the equator. We've got low pressure because air is lighter and it's rising. Okay, well, we can see that air is rising. So this has explained to us what's happening with the Hadley cell. Okay, now if air on the equator continues to permanently rise, so here, sooner or later they're gonna run out of air. Okay, so we need to have more air coming in from the surrounding areas to plug that gap. So that's where the air from the deserts that's sinking needs to travel down towards the equator. Air from the 30 degrees high pressure, where there's air that's sinking, needs to plug in that gap there. Okay, so the air is constantly moving around because of this. It rises, it spreads, it condenses, sinks back down, and goes back towards the equator. Okay, and this is all driven by the fact that the equator has the high level of solar radiation, which is causing that air to move in that form of convection that we can see. Okay, so if we transfer this towards the ferrule cell, okay, so air on the high pressure system, 30 degrees, it is sinking down. This warm air from nearer the equator also spreads upwards. Okay, so it goes in both directions. Now, where they meet on 60 degrees latitude, got another air front. I'll do this as a light blue, coming down from the poles. Okay, because on the poles you can see that we've got air sinking, and this is the same on the southern hemisphere, so therefore we are looking at high pressure. It's a high pressure environment because air is going downwards. So we've got the same thing happening here. So 60 degrees is roughly where we are, okay? And we can see us just there. So air is sinking at the Arctic, which means there's not going to be much precipitation. It's basically just a cold because of the latitude, the fact that it's further away from the intensity of the equator. But we can see air is sinking, so it's going to plug in that gap where air is rising. But here, at this point, we can see that we've got air rising where we get warm air from the south and the cold air from the north meeting. Now this will cause air to rise, but it'll be a little bit different. So warm air from the south meets cold air from the north. So this will still cause air to rise, but this time you've got the heavier cold air and the lighter warm air. So the cold air will always hug the ground. The lighter air, the warm lighter air that can carry the moisture, will rise above it. So when these two air fronts meet, they create what we call frontal rainfall. Okay, so in this place, we can see that where air is rising, it's low pressure, we're going to find that clouds are created there. They'll gradually lose energy and rain itself out, and our air, which now has no energy, will move. It will move along. It will spread out against the atmosphere, so constantly warm air rising, spread out against the atmosphere, and it will sink when it loses its energy, which happens to be 30 degrees on this high pressure system, and the polar high pressure system there as well. Okay, so air is sinking, so no clouds are being created there. So this, just to highlight, and we'll just do it so we've got warm air meeting the cold air. When they both meet, they create frontal rainfall. So air still rises, it's the warm air that rises over the cold air. So I'll just add this bit there. This is when warm air and lighter air rises over cold, denser air. We'll just move a few of these things, just slightly, just so it makes it a little bit clearer. Okay, so this is what we're looking at with our global air circulation. So what we're going to do is we'll just come off of this. Okay, there's quite a lot of information there, but hopefully going step by step makes it clearer. We clear all of this, and what we'll do, we'll see if we can match up some ecosystems alongside it. So we've got these different ecosystems. So it'd be really good to match these up. So take a little bit of time just to think about where they might go. Obviously, you can probably work it out, but just think, what kind of pressure system do we have and where might we find it? So I will do my blue as high pressure. So we can see that there's ice there. We probably know it's near the poles, okay, but we know we're looking at the polar cell. Now we can see clear skies as well. So we know that air is sinking because you'll find clouds where there is low pressure. So this is going to be, we'll put it down as the Arctic. So it's part of our polar cell, and we therefore know that it is high pressure, which means air is sinking. So therefore, there's going to be no clouds or rain. Okay, we take our next one, our desert ecosystem. So what I'll do, I'll match that just down here as well. Our desert ecosystem, we would say it's going to be 30 degrees because air is sinking. Clear skies, no clouds about here, okay? Desert, it's going to be found, so we're looking at where the Ferrell, so the Hadley and Ferrell cell meet. Okay, so it's where the Ferrell cell meet, okay? And in terms of what we expect here, okay, this is a high pressure as air is sinking, and there will be no clouds or rain, which creates our desert. Okay, which brings us to our last one. Looks like the rainforest here. So we are looking here. Okay, we can see clouds, we can see moisture. So this is our rainforest. This is found the center of the Hadley cells. I'll just put on the equator next to it. Okay, this is a low pressure area, which means see less dense, warm air is rising because of that proximity to the equator, the high solar radiation from the sun. So warm air is rising, which creates clouds and rainfall. So hopefully that ties in the global air circulation quite nicely. Obviously, our mild, sometimes rainy weather, we would be looking at another low pressure environment, but we are looking about here, okay? So where our weather is made up, it's made up of frontal rainfall, where the warm air from the south and the cold air from the north meet. I'll just put UK there. So what we'll do, we'll just clear these and we'll just have a quick recap. So looking back at our initial takeaways to describe the movement of each air circulation cell. So we looked that they were made up of the Hadley, Ferrell and polar cell. Low pressure tends to be found on the equator. As air rises, it spreads on our atmosphere and sinks as high pressure on the desert environment, where it doesn't rain and you'll normally find clear skies. So to explain what climate is like and why it's like that, well, where air rises, we're going to find rain. Where air sinks, there's not going to be any rain. Okay, and latitude will determine the temperatures. So that's why further away from the equator, you'll find the polar environments instead of the hot desert environment. And then we've linked to some biomes that are found at different latitudes. So on the equator, you would find the rainforest. Where air is sinking, so the high pressure environment, you would find a desert, either a hot or cold desert, but a desert where it's going to be void of plants or life. Not much can survive there. Okay, thank you very much for watching. Have a good day.